Alright, this is the second video on the introduction to chapter 5. Now we're going to see how a series and parallel circuit behave. So we're going to have a look at the voltage in the circuit, the current in the circuit, and the equivalent resistance in both circuit. So first, let's have a look at this series circuit. So when we say a series circuit, in reality, it's a circuit where the current has only one path to follow. So if we were a charge moving in that circuit, you're forced to move in that direction. Now, by the way, from the point of view of the battery or the power source, like I mentioned, it is pushing the charge. We are always looking at the direction of the positive charge. I know that in many circuits, it's the electron that is moving the electric force. However, most circuit has been built considering the motion of positive charge, and we are going to keep that notation. So a positive charge will be moving in that direction. So the voltage is pushing the positive charge up, and it is moving around the circuit. It has only one path to follow. Now, the voltage here create a difference in voltage above and below the power source in this case. And let's say if it's a certain voltage, V, well, an electron starting here, moving through the three resistor, will come back at this point having lost all its energy, all the energy that the battery gave it, all right? So the total voltage here has to be equal to the voltage drop across the first resistor, plus the voltage drop across the second resistor, plus the voltage drop across the third resistor. So the total voltage is equal to the voltage across each resistor, the addition of them. Now note, I use V1 for the voltage drop at the first resistor, V2 for the voltage drop at the second resistor, and V3 for the voltage drop at the third resistor. Now note, in reality, it is a drop in voltage, so we should be writing delta V1, delta V2, delta V3. However, just in the name of simplification, I'm only gonna write V1, V2, V3 in this case. All right? Now, oh, there's actually a mistake over here. So the current going through each resistor is exactly the same. It has to be. Each electron moving in that circuit has only one path to follow. So the same amount of electron moving in R1 will be the same as in R2 and in R3. So the total current is equal to I1, is equal to I2, is equal to I3, and again, 1, 2, 3 denote the current through each resistor. Now, you've probably seen in the note, and we are going to solve many examples regarding this. There's a way to simplify the circuit. So there's a way to simplify a series circuit and later on a parallel circuit such that we only have one power source and one resistor. And that one resistor will take the name, the equivalent resistance. So in the case of a series circuit, the equivalent resistance is simply the addition of all the resistance. All right, we are going to see in another video the combination of parallel and series, but first I should talk about the parallel circuit. So in a parallel circuit, we have a power source, and instead of the current having only one path to follow, now it can follow many different paths. So an electron being pushed or a charge being pushed from the battery can go into R1, R2, or R3, all right? Now, that created an interesting situation because if you look, the voltage across this wire over here does not change. There's no voltage drop in the wire. The voltage across this wire is also the same. That means across all the resistor, we have exactly the same voltage drop. That means, actually there's a mistake over here, so V is equal to V1, is equal to V2, is equal to V3. The voltage is the same because they all share the same two wire and there's no voltage drop in a wire, remember. Now, the total current is a bit different than in a series because the charge can go in each of the three resistance. Now note, once a charge, let's say, go from the battery into R1, it does not go back and move into R2. It has to follow a drop in voltage. So there will be a drop in voltage across that resistance over here. So the total current has to be equal to I1 plus I2 plus I3. Now the equivalent resistance, to do this derivation, it will be better to see from the conductance derivation. I'm not gonna do it in this video. However, we can simply use that the equivalent resistance is equal to 1 divided by the addition of the inverse of each resistance, of the addition of each resistance, all right? So as I was saying previously, we are going to see in some example mixed circuit that combine series part and parallel part. And really to see how we need to deal with these type of circuit, we need to see an example. It's not a good idea to explain it just in a summary like this. So in a couple of videos, we're going to solve some example regarding mixed circuit. All right. So in the next video, we are going to talk about Kirchhoff's law, and then we're going to be solving some example to put everything together. So see you in the next video.